First of all, we'd like everyone to have the opportunity to place a nomination for the Hugo Shuck Best Paper of the Conference Awards. We have forms available at the registration desk. So if you've seen a paper or two that you think deserve consideration for that award, please drop by the registration desk and fill out a form. Also, I want to remind both the session chairs today and the presenters that there are best presentation of the session awards. So the chairs will be naming a best presentation in each session, and the presenters can drop by the registration area sometime after the session to check and see if you've won the award, and if so, to pick up a memento for that. Another reminder, we have a special midday session from Theory to Wall Street that's from 12:30 to 1:30 in one of these ballroom sections. So just show up over here at 12:30 and you'll be in the right place. Okay. The plenary speaker for today's session is Richard Braatz. Richard got his BS from Oregon State in chemical engineering and his PhD in chemical engineering from Caltech, and then did a year of postdoc work at DuPont, studying polymer film extrusion and some related topics, modeling control related to that. One of Richard's main area of interest is large-scale systems, and he's pretty serious when he talks about large-scale systems. If it's not 10,000 or 100,000 nonlinear partial differential equations, he doesn't want to deal with it. Richard, for a young man, has published a lot of books already. He's published one textbook and 2 monographs. A focus in recent years of his work has been microelectronics and pharmaceutical crystallization problems. And he's received numerous awards already. I'm not going to cite them all. They're in the bio sketch, they're in the proceedings. But the main one associated with ACC is he is the winner of last year's Ekman Award. Without further ado, I'll turn it over to Richard. Thanks.
Thanks, Wayne. Very kind. Today I'm going to speak on challenges, theory, and applications in process control. So I have worked on a few problems. Probably most of my efforts were involved with large-scale systems, which were closely related to computational complexity, sort of on the theory side, to use that to guide the development of algorithms as well as how you would formulate the problem, the original problem you're trying to solve. Worked on multidimensional realization, which is used to try to translate systems into a form amenable to analysis. This becomes a big issue when you're dealing with large-scale systems because you can't do everything just by hand calculations. I then worked on fault detection and diagnosis of a variety of large-scale systems, mostly focused on data-driven type approaches, because that's where the most development really needed to be done. And I've done various things with LMIs and BMIs. I've also worked on a variety of applications from polymer film extrusion and paper machines, in which you can have outputs or measurements on the order, on the highest end, maybe even to 10,000 or so. And any sort of reasonable state equation is leading to very large numbers, so many, many thousands of states. Whole chemical plants, which has a similar situation. And then also for some systems which are not large scale in terms of the numbers of sensors per se, but in terms of the amount of data and the complexity are quite interesting. One of the things that I've also done is to apply our techniques to very complex simulation models or to real systems. And basically, these are just links to show where we've applied various things to various systems, either in practice or in very, very detailed simulations, sometimes both for the same problem. Now, when I was thinking about describing this talk, and I was looking through what I'd worked on, I felt that there are several approaches I could take. So one approach is to try to create one talk to cover everything and spend about 3 or 4 minutes on each, and then have a lot of citations to every paper I've published. And I decided against that approach. Instead, what I decided to do is just focus on a couple of things, what I've been working on mainly for the last few years, which is in crystallization and microelectronics. But to try to discuss this in a way that puts it into the context of chemical process control and try to do this in a way to point out the challenges, both in theory as well as the inherent problem itself, but also to clear up a lot of misconceptions about what really goes on, or does go on by many people in the chemical process control field. So the first question is, why even study process control? Very often people have images of, level in a tank problems and think that that's really what all these chemical engineers are doing. That's not quite true. It turns out that many of the drivers for continued world economic growth depend on improving the control of complex chemical processes. So not simple level in a tank, but very complex processes. One example is pharmaceuticals, which had sales last year of about $150 billion per year, and growth of 10 to 20% per year. And microelectronics, which had sales last year of $200 billion per year, and growth of about 20% per year. And what's well known by economists is that our world economic growth is really governed by just a few industries that's really growing fast. And the rest of the economy is growing relatively slow, or not even growing at all, sometimes shrinking. And it turns out that those aspects of the economy, or that part of the economy that's really growing fast, is the part that really depends on understanding and controlling complex chemical processes. Well, it turns out there are many challenges here. Now, the processes I'm going to talk about here is going to be focused mostly on just this set of complex ones where work needs to be done. And one of the issues associated with model uncertainty. And that's associated in part because of the high complexity, but also in part because of the limited information from measurements. Now, this is improving. I'll give some examples where you can see that that's improving. But to in some situations, it's still essentially true. So it's still essentially true in that you can't really measure the states for the system. You can only measure some sort of surrogate variables. Third, there's complex nonlinear dynamics. Chaos, multiple steady states, and so forth. It has been described in the chemical engineering literature for decades. It shows up in all kinds of things from reactors to distillation columns to crystallization processes, which I'll be talking about. There's high dimensionality, usually infinite, large numbers of partial differential equations that are coupled, that have to be solved simultaneously, and are highly nonlinear. And then it's non-trivial to just simulate the model equations. So even just simulating the equations can be quite a challenge. So those are the type of chemical processes that I'll be mostly alluding to in this talk. I'm going to give two examples. One will be crystallization. I'm going to spend most of my time talking about crystallization processes. But many of the things I'm going to say, I think, has much broader impact or implications into other areas. And then I'll talk very briefly about microelectronics. I won't have so much time to talk about it. But I basically want to point out some systems theoretic issues that I think are really issues that people aren't really looking at, but I think are very, very challenging. And I would like to have some help. And then we'll finish with some concluding remarks. What I have here on the right is actually showing you what these crystals look like that I'm going to be talking about. These happen to be some pharmaceutical crystals for a process that we had when we were collaborating with a pharmaceutical company. And this is a scale of 200 times. So we've scaled everything 200 times using a microscope. And what these looks like, it looks like a bunch of needles, and that's actually what they are. This is a pharmaceutical compound. It has a molecular weight over 1,000. This basically consists of a large number of needles made of crystalline material. So it's a bunch of atoms that are lined up to form a crystal. If you look closer under the microscope, these aren't exactly needles either, they're needle bundles. So there are a variety of very small needles that are actually cemented together by solute molecules. Now, not all crystals look like this. There's a huge variety of variations of all kinds of sizes and shapes, of all kinds of variations, from spirets to cubes to agglomerations that are very bizarre, as well as these sort of embedded needle clusters as I show here. And that's basically the kinds of product that I'll be talking about when I talk about crystallization processes. So we have a picture of the product. The reason you need the product in this form is that you need to be able to purify it. That's very important, and I'll talk about that briefly. But also delivery. So all the tablets that you consume, much of the inhalers, you're actually consuming it in particulate form. Okay, it's produced by this process. Also, when you deal with a lot of things you consume, for example, in pharmaceuticals, you go through multiple stages of processes in which you form crystals, that look at something along these sorts of cases. So different shapes and sizes, but still in crystalline form. This is what the process looks like. Now, usually I like to use industrial pictures, but industrial crystallizer is steel, or you can't see what's going on, so I just took a picture of one in my lab. This is what the process actually looks like. What we have here is a glass vessel. We have it here as just a jacket. You can see the bottom of it here. There is the top part of the vessel, so it's filled with glass. That's the top level. What we have here is a mixture that's inside. All of this whiteness is a bunch of very small particles on the order of microns or hundreds of microns that you can see that's basically reflecting the light. There's a lot of these crystals at the bottom. Usually the density is higher, so you collect at the bottom, and then there's just less and less. You can see that it's not really totally uniform, and that's because there's a lot of turbulent fluid mechanics which occurs inside of here. And at the top, there's actually very little crystals that are actually up there. The stir is basically designed to try to keep those crystals moving in there. You don't want them to get down and sort of cement and get stuck at the bottom of the crystallizer, as well as ruining the crystal size distribution, or the size of the crystals, which I'll talk about shortly. So that's basically what the process looks like from a schematic point of view. Here's a schematic of it. Here's the cooling water, which is coming in. It's coming out, showing here. Most of the processes that I look at are the more complex ones, which are all run in batch mode. We have here, not only can we control the temperature, we can also add solvents. Usually they're called anti-solvents. We can also draw a vacuum on the system. And you can see here that here's our liquid solution with our level, and what you see here are various crystals. Now, these aren't just scale. I've scaled it up so it looks like crystals, so you can see a variation in size and shape. If you actually drew it to scale, these would be little pinprints. You wouldn't really be able to see it on the screen. And there's also large numbers of them, as you can see over here. So billions and billions and billions, to quote Carl Sagan, for example. And what I have here is these anti-solvent and vacuum and cooling water, either separately or in combination, is used to produce what's called a supersaturated solution. And what that means is that the solute concentration, or the solution concentration, becomes higher than it would be at equilibrium. And that drives a kinetic process, or provides a driving force for the solute molecules to move from solution and transport itself to these crystals, okay, to be incorporated into the crystals. So solute molecules will basically diffuse to the crystals, and then they will diffuse along the surface of the crystals and then be embedded or incorporated into the crystalline structure. That part of the process is called crystal growth. Crystal nucleation is when the solute molecules get together to produce new crystals. And the process, in terms of dealing with control, is try to figure out how to add the solvent addition rates over time, set the initial conditions, for example, what are the crystals that you start with, as well as dealing with cooling water vacuum changes throughout the process. And again, the whole thing's well mixed to keep the crystals suspended. Now, the goal of this thing is to control the crystal size and shape for the distribution of crystals. So we've got billions and billions and billions of crystals, and we want to control their size and their shape in solution. And together that's called the CSD, which stands for the crystal size distribution. So that's our goal. Why is this important? Well, for efficient downstream operations, we need to control a crystal size distribution. Now, you're going to have to take that slurry, you're going to have to filter it and wash it and dry it. And if you don't have the crystal size distribution set correctly, those processes will become uneconomical, just too expensive for the process to be workable. And this is true even for pharmaceutical industries, where I've seen cases where a messed up CSD, basically, or poor crystal size distribution, has made a high value-added pharmaceutical unprofitable. So even though it's high value-added, it made it totally unprofitable. And so this is a case where even in something high value-added, you really need to control that crystal size distribution to be able to do the downstream processing. There's also safety, purity, so you don't want to be incorporating other molecules inside your crystals that you may not want consumers to be consuming. They may not be too happy about that. The FDA will certainly not be too happy. And then you have product effectiveness, and I'll give two examples. Most of what I'm going to talk about is pharmaceuticals, so we'll use that as one of my examples. Basically, tablet stability. The way you're going to form tablets that you're going to be consuming, so whenever you get a headache or whatever, is you'll take a variety of crystals formed by this process of different types, you'll put them together, and you'll compact them. You'll squeeze them together under very high pressure. If you have the crystal size distribution incorrectly, then when you compact them, the crystals will actually fall apart. Okay, they will not retain its integrity, which of course prevents you from controlling your dosage. And then there's bioavailability, and that has to deal with the rate at which your body incorporates the drug into your metabolism. And that's given, again, by the crystal size distribution. Size, because small particles tend to dissolve very quickly in your stomach, as well as, whereas big crystals don't. But also morphology. Some crystal forms are almost completely insoluble. And so if you end up accidentally making that form in your drug and people consume them, if they're insoluble, they'll just pass totally through your body. You won't even see the effect of the drug. The other issue with pharmaceuticals and effectiveness is that many of these drugs are incredibly potent, and they have pretty nasty side effects. And so we've all seen the commercials on TV where the list of the side effects is longer than the actual advertisement for the drug that they're trying to advertise. If you actually look through the back of your drug and read it carefully, you'll see that most of the text, again, is towards the side effects rather than the actual therapeutic benefit. And so what you would like to do in that sort of situation is to control that crystal size distribution to maximize the therapeutic benefit of the drug while minimizing nasty side effects. And then in photography is another example where controlling crystal size and shape is very important. And basically, the image quality, the quality of the image is governed by silver halide crystals, which are embedded into the film. It's completely governed by that. If you mess up the crystal size distribution there, you've got crappy images. If you want to get better images to really try to provide, let's say, provide a competitive edge against digital photography, for example, then you need to have finer control of crystal size distribution. So now I'm going to talk about measurements. Now, the measurements that I'm going to talk about does emulate a pattern in chemical process industries, and that is that in many industries we're starting to be able to measure much more than we were able to. So instead of just having temperature or pressure, we're able to measure more and more. And what's happening is the high value added, we're getting the sensors very quickly, and then slowly percolating to the other parts of the industry. Crystallization, I would say, is probably at the top where you've had the most sensor development. The other reason I'm going to talk about these measurements in some detail is not just because they're cool, but also because I see, and not just because it emulates a pattern that's occurring in the chemical process industries, especially for complex processes, but also because if you're looking on systems with fluid particle type systems, you may be able to actually use these in systems that you're interested in. And they seem to be not very well known outside of the chemical industry, or the engineering, or the pharmaceutical industry. Now basically, what we generally do is we look at state-of-the-art commercial instrumentation. Now we have to characterize the solution phase, or the concentration in solution, because that's going to affect the entire kinetics of the process. And for that we'll use a technology known as ATR-FTIR. And I'm not going to define exactly what each of those terms mean, I'm only going to describe what it means from a control perspective. The second thing we have to do is we have to characterize the product, or the crystals, or the crystal size distribution, the CSD. And for that we'll talk about a couple of techniques. One is laser backscattering, and one is video microscopy. And these sound like very fancy techniques, but these are actually commercial instruments that you can use out there in the plant, and you can use them, hit them with a hammer. It's not advised to hit them with a hammer, but you can hit them with a hammer and they'll more or less work. So they're reasonably robust instrumentation. Where I'm showing you here is the video microscope. Basically, this is a stainless steel rod. That's the important part for the control in the sense of understanding the description. This basically is a big block that has a bunch of electronics in it, as well as a laser light source connected to a cabling and more electronics. The final part that you see at the end is a metal rod about 1 inch in diameter that you insert so that its tip, which is actually right down here, is directly in the crystal slurry. Now, I'm not showing the crystal slurry here because I want you to see all the sensors, but normally the slurry would be up to about this level, and so this would be stuck right into the slurry. So the tip's about there. And basically that allows you to take snapshots of the crystals in solution to actually get pictures, and I'll show examples of that. It's very important to the system. These crystals are semi-translucent, so you might think it's impossible to measure anything. We'll show that yes, actually it is possible to actually measure a lot, at least a lot in some sense. And what I have here is a laser backscattering device where we shine laser light forward and we collect the backscattered light off. Again, it's a metal tip which is located in the crystal slurry. And then we have the solution phase, which is an FTIR ATR spectrometer. This is shown over here as a box. It has another probe, that's the important part in terms of control. I can stick this directly into solution and measure the properties of the liquid phase. Now, if you have any sort of fluid type system, I would seriously consider looking at these type of technologies. Basically, first we have the ATR-FTIR, allows us to measure the solution concentration. That's important because all the kinetics is governed by the solution concentration. Here's our crystallizer, and we have a probe that's stuck in right here. There's the tip. And what this probe allows you to do is allows you to measure the infrared spectrum of the fluid in contact with the tip. Now, a spectrum, from a controls point of view, you discretize it, you just get a vector, so it's a vector of numbers. Each of those numbers is basically the amount of infrared light at that frequency that's absorbed by the chemical species in contact with the tip. Okay, so that's basically what it is. It's a vector of information that characterizes the chemical species in the system. We have a negligible signal from the crystals. That's why this is a major advance. In the past, you would get a lot of problems where the solid phase would mix up what you're seeing in the solution phase, so it's very hard to figure out what was going on. You can show with some fairly simple physics that you don't get a signal from the solids, only the liquid phase signal. It's applicable to multi-component systems because I get a vector of numbers at every sampling time. I get a lot of information I can use for characterizing the solution concentrations. And one of the things that we showed by using a combination of robust control type ideas as well as some types of statistics that you use for rank deficient estimation problems is that you can actually get very high accuracy with this instrumentation. And so one of the big issues that was associated with here was had to deal with how do you deal with that large amounts of data and how do you get very, very high accuracies. And basically an idea of using robust control with multivariate statistics was fairly useful. Now we'll go ahead and talk about the laser backscattering device. That's what I have here on the left. If you have any type of particulate system in which you have particulates that are bigger than 1 micron, this is the type of device you're going to be looking at. What we have here is a fiber optics. This is the stainless steel probe that I was showing. Here's the rotating optics that's moving across here. Laser beam is basically coming to the rotating optics, which is focusing that laser beam down to a point right at the tip of the probe. This section here is where we're showing the crystals or particles. I've blown them up so they look bigger than they actually are. They're really on the order of microns. And the reason you have these rotating optics is that you're going to pass this focal point around at very high speeds in a circle. And what this is going to allow you to do is when that beam hits a particle, you'll then collect the backscattered light. And you'll say, aha, I see a particle. And then when the beam passes across the particle, you'll still collect backscattered light. You'll still say you see a particle. And then it hits the edge of the particle, you no longer get a reading, and then you know that you've completely passed across the particle. Because you know what the velocity in which the laser beam is moving, and you know how long it was that you received backscattered light, you put that information together, you get the length across the particle. Notice I'm not showing the optics for the collection device, just the part that's actually emitting things, and that's because it would be too complex to try to also show the optics for collection at the same time, but they're all fit in here as well. So that's basically what the device is. Here's an example of the kind of data you get. Basically, the chord length is that distance across the particle that you measure, and in this case, it's in units of microns. We have here the counts per second, and this is basically a histogram where you count the number of particles within a given size range. So, for example, this point is about 95 particles were counted within a size range of about 1560 microns. Okay, so that's the kind of information that you get. This is a far cry from measuring just temperature and pressure, which is, basically what we did have that was available. But it does pose a lot of challenges for estimation, and that is you get huge amounts of data. This was collected in 5 seconds, so very, very large amounts of data you can collect to characterize the crystal particles. But there are some sort of weaknesses. So here's where we actually have a picture. I'm showing, zoomed everything in. On the length scale of particles, the laser beam is moving. You can't see the radius of curvature, basically. This isn't a laser beam moving from left to right. What it is a laser beam where you're looking at it. So treat your eyes as you're looking at this picture as though those are the laser beams that's focused onto a focal point. And so your eyes are looking at it, and you're looking straight in it as though that's the laser beam. okay? Then as you move along here, you're moving across, and you see, aha, okay, I'm collecting backscattered light, so I see a particle. And then you've crossed some threshold that says, I see a particle, you see a particle, you see a particle as the laser moves. And then you get near the edge, and then you no longer collect backscattered light. And then you say, okay, past the particle, I know how fast my laser is moving, so I know the velocity, so that gives me the duration. I know the amount of time, I can calculate what this distance is. Well, one of the challenges to deal with this kind of data is one issue, and that is that you've averaged over all the shape information. So even though you're able to get a vector of very high resolution with a large number of elements to characterize the crystal size distribution, all the shape stuff's been averaged because whatever you measure depends on wherever the particle was and what its rotation was. So if I take the same particle and I just rotate it 90 degrees, you'll get the chord as this distance, this long distance, instead of getting it as this narrow distance, okay? Similarly, if I happen to just caught the edge of the particle, if you take this particle and move it down and rotate it a bit so I only catch this edge, that's the reading you'll get. You'll just get that edge. And so it's somewhat of a challenge trying to back calculate what the shape is. And you can show with some fairly simple information theoretic like I did, you can show that it's impossible to characterize the shape uniquely from the kind of data you get from laser backscattering. So there is shape information, but you can't characterize it uniquely. So you basically get another rank efficient estimation problem. And so what that's done in recent years is motivated the development of sensors for 2D crystal size distribution. In other words, you can get both you get information on multiple characteristic length scales, which is what is needed to characterize shape distribution. So that's what I'm going to talk about next. I'm going to focus on the commercial instrumentation. And this is video microscopy, where we're taking pictures of crystals in solution. And that's what we have here on the left. We have 600 microns by about 900 microns across. You can see a crystal particle in solution right here. It's actually quite a bit better on the screen than what you're seeing up there, but you can see that there's a crystal particle here. It's a rod-like crystal. We have another crystal along here. There's another crystal behind this original crystal that's over here. You can see the aspect ratio of the crystal is about 5 to 1, so this distance is about 5 times bigger than that distance, which is across. There's actually another crystal which is located off here. So even though the crystals are semi-translucent in the fluid, you can actually take pictures. So you might think, okay, this is great. I can get size and shape very easily now, because now I can take pictures. I can collect data very fast. You can actually collect gigabytes of data very quickly. You get 10 to 30 frames a second, where each of these frames is a very reasonably large matrix. Unfortunately, the contrast is too low for direct image analysis, so I'm sort of showing you the best picture I could get, essentially. The other images tend to even be worse. You get a lot of blurry mixtures of grayscales, etc., so you can't directly image it, even though you can get a qualitative feel. What's been able to solve recently is to get those gigabytes of data, take that information, use some advanced image data reduction-like techniques, combine it with some ideas, basically for robust control sort of ideas with multivariate statistics for ranked efficient problems, and actually get size and shape distribution information. And so that's the kind of thing that's now starting to become available, at least for some of our more interesting or complex processes. So I've talked a bit about measurements. If you do have fluid particle systems, I would suggest that you do some consideration. You have to use that data for identification. And I'm going to only give you the simplest model that we use, just to sort of simplify the presentation. I mentioned that the models tend to be reasonably complex. This is the simplest form. Basically what we have here is a material balance for all the crystals in solution. We have to use a distribution because there's so many, we can't characterize each crystal individually. This is basically a standard material balance. We have kinetics. These are the kinetics. The G1 is the growth rate associated with the R1 direction. That's one of your characteristic length scales to characterize the size of the crystal. G2 is the growth rate in the R2 direction. It's also a function of time for the batch process. We have the growth rates for the two directions, and you have the nucleation rate, which is the rate of the production of new crystals. And all of those kinetics must be characterized in the system to be able to represent this crystallizer or to model this crystallizer. And you can see the kinetics show up here. They're described by highly nonlinear equations that are functions of the solution concentration as well as temperature. There's also some integral partial differential equations and nonlinear algebraic equations that also must be solved simultaneously with this equation. And our goal is to estimate the kinetics. But it turns out it's actually a little bit more challenging than that. And that has to deal with the needs of the pharmaceutical industry. And what happens is that when you're dealing with a drug, you have multiple layers that must be passed. Where you get through a certain trial, and then you have maybe 1,000 type drugs, and they don't pass the trial, you go through the next trial, you go through the next trial, each time winnowing out the number of candidates to hopefully something that's going to be successful and make it to the market. And to do that, what's important is to be able to do your entire scale-up process very fast. And that's because at the point of time where a control engineer might make an impact is after the drug has been approved by the FDA. And at that point, you need to scale up the process as fast as possible. Okay? So as soon as FDA does an approval, sometimes even during the approval process, you have to, as quickly as possible, start from a beaker and go all the way to your final optimized control process as fast as possible. And that's for two reasons. One is that there's a length on the patent. So every day you're not producing that drug is a day where you've lost all the value of the money. Okay? And so once you get to the length of the patent, the generic companies come in and you lose almost all your profit. So you basically have to, as quickly as possible, get the process up, just because every day you're losing money. So every day you don't have the process up, you're losing money. The second reason has to deal with it's partly psychological, and that is that if you've developed a drug, or pharmaceutical companies developed a drug for a new therapeutic benefit, whoever's first to market wins about 70% of the market on average just by being first, not being best. Okay? So if you develop the drug first and doctors start signing it out, they will tend to keep signing it out even if a better drug comes along, unless it's much, much better. Part of it is they have more experience with it because they've had the effect of patients. Part of it is that they're just in the practice of signing out that drug. So the time to market is a critical issue here. So you want to be able to do this entire identification process, if possible, in something like 2 experiments. Okay? So we're talking a pretty interesting problem. Highly nonlinear partial differential equation, multiple kinetic parameters, and you want to get everything in 2 experiments. So what do? Well, we have to do everything in batch mode, because we have to collect a lot of detailed dynamic information where we can really track through the state space to a large degree. We do some experimental design. We design an experiment. We put it to an automated experimental apparatus that has all those sensors I showed earlier. You collect a bunch of measurements, that's the vector Y. You feed that into a parameter estimation scheme. You estimate the uncertainty in the parameters. That actually is pretty important to industry in this case. They don't just want to estimate how good things are, they want to actually know how far you could be off. We usually use Monte Carlo approaches for this, but there are other techniques like sensitivity equations. We then ask if the model is accurate. If it's accurate enough, then we stop. If it's not accurate enough, you repeat the procedure. People familiar with identification would be reasonably familiar with what I'm talking about here. It basically is that everything's done through these highly coupled nonlinear equations, highly nonlinear partial differential equations. And then the second thing that you have is what happens if you actually get it accurate enough. If it is, you feed that into a robust optimal control design algorithm shown here. You can take into account implementation uncertainties and then compute your final design. That optimizes over all your initial conditions. It's basically like classical optimal control. So all your initial conditions and all of your operating variables, and then you can even do all of your feedback controls that you're going to have embedded into the system, overall control system. Where were the big challenges? One of the big challenges was down here, and that is how to deal with nonlinear distributed parameter systems and rigorously quantify the effect of model uncertainties. One of the things that we did also that I think is somewhat interesting, maybe interesting to the identification community, we've actually been able to use this information to change the way we do our experimental design. And basically what we do is because we can characterize the effect of the uncertainties on the actual performance, we can feed that information back to the experimental design procedure. So instead of using like de-optimal design, which just minimizes the uncertainty in each experiment, we can actually try to optimize the performance directly in our experimental design procedure. So design experiments that are good for performance. It turns out that's very important for crystallization, we found. And that's because some of the parameters have very similar effects. And so some types of uncertainties are like really important and some don't really matter. Okay? And so it's important to actually not just focus on uncertainty, because a lot of the uncertainties don't really matter, only a few are critical, and to use that performance objective to shape the way you're going to reduce the uncertainty to design better experiments. We've actually been able to do on pharmaceutical systems, be able to get fairly accurate parameters in only 2 experiments. So So now I'm going to talk a bit about simulation. The simulation stuff I'm going to talk about is going to be, I think, is important to people that work with systems in which you have conservation equations. So one example would be fluid particles, compressor systems, and so forth. I think it's going to be fairly general. So I'm actually going to spend some time on it because I think it could really impact control. One is that there's significant nonlinearity model complexity. There's a wide range of time scales and length scales. The classical finite difference algorithms are too slow or too inaccurate for the type of sharp distributions that occur in practice. When you nucleate new crystals, it really creates sharp shocks to the system, to the numerical algorithm. So it's very important to be able to deal with those. What we've used a class of high-resolution algorithms that provide high speed and accuracy. And we got this from the computational physics community. Now, this could make major impact. So if you're looking at systems with conservation equations with sharp changes, for example, compressor-type systems or fluid flow-type systems, or even systems perhaps in microelectronics industries, another example. Systems in which you have conservation equations, these algorithms can very incredibly, so orders of magnitude improvement in speed and accuracy. And the reason that's useful is that now we can get things fast enough we can control by solving the original simulation equations. So skipping the model reduction step and just going right in and solving the original problem. And so I'll give an example. This is multidimensional crystals. These are Braatz crystals for some systems in our laboratory. On the left shows a single crystal where we have two characteristic length scales, length and width, which equal to breadth. Here we have the crystal size distribution. These are for seed particles that we're going to start off with in the crystallizer. And those seed crystals will make the crystal size distribution much more reproducible. The simulation equations have greater than or equal to 3 independent variables. People familiar with PDEs know that each independent variable you add adds an order of magnitude or 2 or 3 to the complexity. We've actually shown recently in a journal, a paper we published in a physics journal, that you really need at least 4 independent variables to really describe these systems. So a couple of characteristic length scales, an external dimension, as well as time, all being independent variables that increase the complexity of the system. I show here the distribution. This is the length distribution. This is R2. We're going to start off with crystals that have an aspect ratio of 1, or about 200 microns by about 200 microns. And this is just a distribution function, as we're familiar from statistics. This is descriptions we had earlier. We have to solve it simultaneously with algebraic and integral differential equations. And it's a little bit more complex than I'm showing, but this just sort of simplifies it enough for presentation purposes. This is actually the result after a run. This was actually done in 3 minutes on a PC. And you can see the kind of resolution issues I was talking about. This is a huge spike of nucleated crystals that are formed. So there's very sharp variations with respect to the derivative with respect to the R1 and R2 direction. These are seed crystals shown in the back. These are crystals that nucleated and grew. This whole thing was done after, this was 2 hours of time in terms of the batch. I'm going to actually show a movie where we're actually going to see this in progress, and I'll describe it in more detail. Before I like to do that, I'd like to give a little more background information. There's the crystal size distribution for Braatz crystals produced by nucleation and growth. This is for a real system. This is not some fictitious simulation. This uses parameters that we computed in the laboratory using the identification procedure I had earlier. We've done the entire batch simulation in 3 minutes on a PC. We've used supercomputers to take spatial variation into account. And another advance that's happened relatively recently is it's getting to the point now where you can use supercomputers with very little effort. You can basically set it up in your laboratory, you can set up a little Linux cluster, a PC cluster, and very easily write these programs, very short programs, to take into account that extra computation. And so I'm only going to show the well-mixed case just for demonstration purposes. Here's the movie. So what you're seeing at time equals, this is set up in a loop, so it's going to keep repeating. At time equals 0, you start off with some seed crystals that start off at about 200 microns by 200 microns. So that's a group of crystals with some variability in the size. And then as time progresses in the batch, I'm increasing the driving force for nucleation and growth. And those seed crystals move, and you can see they're moving off favorably in the length direction. That's why crystals form rods, is that you have a higher growth rate in the characteristic direction or axis associated with the length. So that's why you're actually forming rods. You have higher growth rates in that direction. So the seeds move off into that direction. Those seeds are needed to produce basically reduce the stochastic nature of this process, as well as to improve the distribution of crystals. The crystals that show up here are the nucleated crystals at very small sizes, so I'm just showing them here on 0, 0, because it's all you can see at this length scale of the image. But the crystals nucleate as a spike, and then they grow. And as they grow, they move off into the R1 direction, as you can see here. So these are the crystals that nucleate at time equals 0 and then grew. These are the ones that nucleated and grew after that. The ones you see here are the ones that just nucleated. So you can see some of the fine variation and very, very sharp peaks that occur in these kind of processes. This entire simulation, as I mentioned, was about 3 minutes. We can solve the entire one with spatial variation using a simple Linux cluster in about 12 minutes. So we can solve a lot of iterative optimization and control problems. Now I'll make a few comments about control, very brief due to time constraints. We've developed an approach to batch optimal control. I referred to it earlier at the bottom, where we can quantify the effects of uncertainties on product quality. We can do this to nonlinear distributed parameter systems, including integral differential equations and algebraic equations. And we've applied it to a variety of systems, including multiple and single crystal growth. Single crystal growth is used in nonlinear optics, so I've done a little bit of work there. There is one limitation: finite time. But if you do have a system which is finite time, then you may want to look this type of approach at. It basically uses an idea of combining some principles with structure singular value and some Taylor series expansions. So there's some ideas from numerical analysis. Now I'd like to briefly summarize this part of the talk. Measurements are becoming available. This is happening in the chemical process industries, and it's especially happening in the high value added complex processes. In control, it's making crystallization control a reality. Fast simulation algorithms are now available. This can be used for all kinds of conservation systems. This opens up the possibility for advanced control. We can now quantify the effect of uncertainties and their effect on extremely complex distributed parameter nonlinear systems, and that opens up the possibilities for robust control. There's been some work by myself and Christofides and Rollins in this area. Then there's control of crystal shape. We can actually do that in solution. That actually is possible now. Patience and Rollins has one example, and there are other experimental demonstrations in the work. So that was the majority of the talk. Now I'm going to talk a little bit about microelectronics processes, basically motivating and opening up a bunch of control theoretic issues that I think are things we haven't really been looking at. But before I do that, I'd like to make a comment about Moore's law. And that is that the number of transistors on a chip doubles every 18 months. This is one of the motivations for looking into this particular industry. What I show here is transistors per chip. That's this blue line. You can see it's a line and a semi-log plot. And over here I have the minimum feature size, which is being reduced as we increase the transistors on the chip. And we basically extrapolated it a bit. You can see right now the minimum feature size is on the order of about 0.13 microns or so. It turns out this is very important for control. So why is it important? Well, it turns out that many people have predicted in the microelectronics industry that high-performance control is needed to follow Moore's law. So not that it's optional, that it's necessary. And that significant limitations to the optimization and control is the creation of fundamental models for these type of processes, these very highly complex chemically reacting systems. I'm only going to talk about two that I have some experience with. One is copper electrodeposition, which is a collaboration with Professor Alkire at the University of Illinois, which is used to make copper interconnects in microdevices. I'm mostly going to talk about that one. We've also done work at fast RAM gravitothermal processing with Professor Seabauer, also at the University of Illinois, and that's used to reduce defects after ion bombardments. That's for doping of materials. In both cases, these steps are considered key limitations to the manufacture of faster devices, and especially associated with getting smaller and smaller length scales required to follow Moore's law. And in both cases, improved models are needed for the control of device properties. And I'm only going to talk about the first one. And again, what I'd like to do is show you a picture of what this stuff looks like. What you're seeing now is copper, which has been deposited into a device. So what they've done is they've taken a material, probably silicon, and they did some etching, so they had some sort of a surface, let's say a trench, And that's, for example, how this was made. And then they deposited copper in that trench. And then they put another layer on top. And then they put another layer on top. So these are layered processes. For each of the layers, they continue to do deposition of material. There's a lot of extra steps I don't have time to really talk about. After they were done creating the entire device or the chip, they then basically dissolved all the other material that was there. So you would just see the copper that was left over. So there used to be a whole bunch of silicon and other stuff in there. They went ahead and just etched that all away. So all you see is the copper that's left over. So you can see it's almost like seeing a chemical plant or something, okay? But this is all just copper, which is all connected. And that's the kind of stuff that you actually have in your micro devices. And so our goal is actually to do that process, the process which does this deposition. And to do this in a way that we have no voids. In other words, this is a continuous stream of copper that's connected. So there's no voids or holes that are going to destroy the microdevice characteristics. Now, the part that we've been looking at is pose all kinds of what we think are interesting control theoretic issues is associated with the simulation of the processes. So even though a simulation is very intimately related to control, it has to deal with the nature of these simulations. The process simulation requires linking continuum and molecular length scales if you're actually going to model this process in any reasonable way. And what I'm showing you here is just a part of it, just to sort of simplify the presentation, where we're looking inside a diffusion boundary layer. This is a fluid layer right on the top of the surface of, let's say, silicon, for example. And what I'm showing here is an expansion where we zoomed in on one region and we're looking inside a trench. So this blue stuff here is silicon. And what I'm here is depositing copper inside this trench, so that's this color. And basically this scale is about 100 microns, the length of the diffusion boundary layer is about 50 microns, the distance across the trench is about 0.13 microns. And what the problem is to deposit this copper in here, the processing problem is to deposit the copper in here without forming a void. In other words, you don't want to deposit all the copper up on these knees and then get a big void space, and it's going to destroy your microdevice properties. But it turns out the copper more naturally is going to go ahead and deposit up here rather than down here, because it takes a shorter distance to diffuse to the surface, to diffuse to these corners than it is to the bottom. And there are various chemical additives to try to even out this process to prevent the voids. From a simulation point of view, the top code is usually a finite difference or finite volume code that simulates diffusion and migration. It has a sampling time of about 5 milliseconds. At least that's from a control point of view. In other words, the integration time is 5 milliseconds. On the bottom, you have a Monte Carlo code, kinetic Monte Carlo. It's a stochastic code which simulates the absorption of molecules as they come onto the surface, desorption of molecules off the surface, diffusion along the surface, bulk diffusion, where you just diffuse to the surface from solution, as well as chemical reactions that can occur out here in solution, as well as occurring on the surface. And all of this phenomena can be occurring in the same process with large numbers of equations associated with each phenomena and stochastic, and all of these are stochastic events that can occur. Now, this happens to be for a 0.13 micron trench. Now, what we decided to do is look at this from a control point of view, and I'm going to tell you why in a minute. This is how the codes look like from a control point of view. Basically, these two codes have totally different natures. The top code is a continuum code. The bottom code is a molecular length scale code. One is finite difference, which is basically large numbers of partial differential equations that are coupled. The bottom code is a bunch of stochastic discrete events in a three-dimensional box or matrix, or lattice is what they call it in the industry. It has a timescale of about 1 nanosecond, the Monte Carlo code. The finite difference code has a timescale of 5 milliseconds. So the way to do this, because you can't make it one code, is you have to write two codes, and you have to get them to talk to each other. And the way they talk is by passing information about the boundary between the two codes. And this boundary is located right at the surface of the trench, below the boundary layer, which is a layer of fluid on top, and the trench in which you're actually depositing copper. And the way you run this thing is you iterate the Monte Carlo code 1 million or so times on the sort of nanosecond time scale. Then you feed information to the finite difference code, which is, you feed information to the finite difference code. That finite difference code does a calculation, say once every 5 milliseconds. It passes information back to the Monte Carlo code, where this information is associated with the boundary condition. Now there's a noise term which I have located on the bottom. That's because it's a Monte Carlo code, it's a stochastic code. There's a lot of noise being driven into it. The information passed from the finite difference code is the mass fluxes, or it's the amount of mass passing to the surface. The information passed from the Monte Carlo code to the finite difference code is concentrations. So it's various concentrations of various species. It's basically a vector. If you represent this in a control point of view, the top problem is just a discrete time nonlinear dynamical system. That's the state space equation. There's a corresponding output equation. This capital T is associated with 5 milliseconds. U of k is the input, X of k are all the states, which is fairly large for the system. The code on the bottom is another code, which is another discrete time dynamical system. The 1 corresponds to 1 nanosecond. V of k is the vector of inputs, which include the noise as well as the signal is being passed from the finite difference code to the Monte Carlo code. So why would I look at this as a control problem? Well, it turns out when you look at it a little bit more, you find out that the top code is bounded input, bounded output stable, and the bottom code is bounded input, bounded output stable. So why did I get involved? I got involved because when you connect the two codes, they're unstable. And that was the phenomena that was presented to me, is that they had two well-conditioned codes. When you put them together, they became unstable. And this was a big mystery, because the people didn't think that was possible, that you could link two stable things and get something unstable. So, and it turns out, of course, as control engineers, we know it is possible. This actually shows you the instability that occurs. I'm plotting just one of the variables that's passed between the two codes. This is passed from the Monte Carlo code to the finite difference code, and this is the copper 2+ concentration. That's the way copper 2+ is basically diffusing to the surface, where it gains a couple of electrons to become copper inside the trench. And you can see that there are stochastic fluctuations that's associated with kinetic Monte Carlo, and then they're growing. And you can see an exponential growth that's occurring there. And so that was basically what the problem was. We said, okay, how do we solve that? Well, we analyzed it from using our control theory. We basically took the two codes and sort of split them or pulled them apart a little bit. Those are the two codes that we had earlier, these nonlinear discrete time dynamical systems. And then we designed a layer in between them, an interconnection layer that conditions the passing of the boundary conditions. What do you think that layer was? It's a filter. Okay, so we basically used a filter to stabilize this nonlinear system. And that's essentially what we have. I'm simplifying it a little bit, but essentially what we have is basically stuck in a filter to simplify, to stabilize the closed-loop system. So now we have stability. However, there are still some issues dealing with analysis. One is that, let me just make a few comments. We treat the codes as discrete time nonlinear multi-rate systems. That's the way you have to treat them, with very wide varying rates. One of the issues is analysis is stability isn't enough. I can get stability with this code, and I can get all kinds of measures of performance from my code with this interconnection layer. But that actually is not what I really care about. What I really care about is the real system. And I have to make sure that my changes to the closed loop system by inserting this interconnection layer hasn't messed up the physics, or no longer describes the physics of the original system. And so that poses all kinds of issues in terms of how do you do a formulation to the physics of the true system when you've added these modifications to the code. There's also a whole bunch of other issues for these systems, including sensitivity analysis, parameter estimation, experimental design, model selection, and nonlinear control. Model selection is an issue because they don't actually know for sure how all these species work, so they have to formulate a series of hypotheses. You need to come up with some clever way of selecting among those hypotheses with the amount of data that you have. I'm going to show you the simulation to show you the result after you insert that filter. It'll also allow you to show the process a little bit. What we have on the bottom is our trench, so this is most likely silicon, for example. These halos are concentration profiles. I'm pretty sure these were copper 2+ concentration profiles. So every line is a line of copper 2+ concentration. I again have this rotating, so it goes through. It'll start at 0, completely fill, and then restart. We start off being empty. You start putting a potential or a driving force that drives those copper 2+ ions towards the surface. These are all the copper which is depositing, and then you start to fill progressively and start to fill. At the end, you can see you get that void that I was talking about, which is bad. So they don't like the void. So they have to deal with how do you design additives or other chemical species to avoid these particular voids. And so that's basically what the simulation looks like when you've applied your control theory. There are many issues here. We've done some initial stuff, but there's not much to be done. We haven't fully characterized, for example, this kinetic Monte Carlo. There are all kinds of issues associated with the kinetic Monte Carlo, including the fact that if you describe it really correctly, you need some sort of very complex stochastic nonlinear hybrid system representation. For anybody who's interested in that can come in and talk to me, because it's very, very complex. But we've made some sort of modest progress. There's also the design issue on how to actually formulate some sort of optimal control problem, design that interconnection layer in an optimal manner. So what I'm going to finish is with concluding remarks. And this is one approach to doing problems. One is to select a challenging problem. What I try to do is I try to pick something that I think that basically probably has no hope of solution, and then I just try to jump in there and try my best. So that's basically one approach that can be taken. Identify the key fundamental issues. I spent a lot of time doing that. I try not to focus too narrowly on feedback control. I often use the principles of feedback control and the tools, but I don't go in and say, okay, this is an H-infinity problem. How do I pose an H-infinity problem? Okay, that's not a good way to make a lot of progress for a lot of these systems. So try to identify the key fundamental issues. Learn or create whatever theory is needed. So you've got your own little tools, try to learn whatever rules. I've taken a lot of things out of physics literature, for example, so take it from wherever you can get it. Certainly no prejudicial nature whatsoever. And the last comment is something that I'm not the first to make. It's certainly been made by many leaders of our field, and that is that the impact of control theorists can be much broader than control theory. And what I mean by that is that I keep looking at problem after problem where control theorists are not working, or barely working. A few pioneers have sort of moved into. And I keep seeing again and again where some control theory could have a tremendous impact, whether it's for analyzing numerical simulation algorithms in development for solving a particular problem, to dealing with analyzing data for very complex chemical systems. And so control theory is certainly very valuable and should be used as one set of tools that can be tackled to all kinds of problems. But control theory in itself is not going to be translated to these other industries. It's going to take people to take that control theory and look at other problems, identifying the key fundamental issues, and then resolving those issues. And that impact can basically, I believe, impact almost every other field of science and engineering. As a few final notes, I'd like to list just some of my collaborators. I didn't have a space for all of them. The people on the left were people that contributed to this presentation, including Professor Alkire, as well as collaborators at Merck, some of my postdocs and grad students. And these are some other people that contribute on a variety of other projects. I'd also like to thank the acknowledgements. These are just funding for this particular material I presented here, which includes the National Science Foundation, which is the SCICE program, National Center for Supercomputing Applications, Semitech, which is a consortium of microelectronics industries, Merck, Procter & Gamble, and DuPont. Now, I'd love to answer all kinds of questions, but I don't think I think I was told that that's not going to happen. But if anybody wants to ask me questions after, I'll be around for the whole day, and I'd be happy to talk about them.
Thanks, Richard, for a very nice talk on some interesting and challenging problems in simulation and control, and particularly interesting coupling between simulation and using control concepts. We have 30 minutes for a coffee break before the 9:30 session. This is also a good opportunity if you want to go to the exhibits hall and buy one of Richard's 3 books, and he'd be willing to sign them